Hi, my name is Isaac Olson, and this summer I researched adaptive control for an autonomous quadrotor helicopter with Professor Ella Atkins and the Michigan Autonomous Aerial Vehicles Team, also known as MAV. MAV competes in the International Aerial Robotics Competition. The challenge requires a UAV to enter a mock security office without being detected, extract and swap a flash drive off of a desk, and exit the compound within 10 minutes. Doing this requires the UAV to be very precisely controlled. At its most basic, all a controller does is analyze information about the state of a system, in this case, a quadrotor with its roll, pitch, yaw, and other measurable values. The controller then uses some preset algorithm to take that information and convert it into the necessary input to drive that system to some desired state. For example, if the quadrotor started to roll to the right when it wanted to stay at a stable hover, the controller would simply increase the speed of the right motor and decrease the speed of the left motor to bring the craft back to its stable state. A quick example of a simple linear controller is a PID controller, which stands for proportional, integral, and derivative. The controller looks at a given value, for example roll, and measures its error from the desired value. This is called the proportional term. It then uses the integral and derivative terms respectively, of that error. Then it multiplies each of those terms by their own tunable constant to create a controller output. A PID controller is a linear controller, which means it cannot fully control a nonlinear system such as a quadrotor in all of its states. This summer, I worked to implement a nonlinear controller to improve the performance of the MAV quadrotor. To do this, I used an Lyapunov integral backstepping controller. This controller uses an inner control loop to stabilize the vehicle and an outer control loop to follow position waypoints. The control law was derived from the physics governing the system and a defined set of inputs, in this case, the forces of each motor. It takes into account the nonlinearities present in the system to allow for a much larger range of controllable states. After I defined the control law, the team had to spend a great deal of time testing and tuning the controller to produce stable flights. I had to convert the form of the controller to allow for more intuitive tuning. I also implemented a moving rate set point, which allowed us to control the rate at which the quadrotor stabilizes itself more accurately. With this controller, the MAV quadrotor was able to achieve stable hover and follow position waypoints.